This is chapter 28, Physical Optics. So last lesson we learned about geometrical optics, which is all about light traveling in straight lines, refracting through lenses, and reflecting off mirrors. Physical optics deals with light as a wave. So geometrical optics basically treats it as a particle moving in a straight line. But since light is both a particle and a wave, it's going to have particle-like properties, geometrical optics, and it's going to have wave-like properties, which we're going to study in physical optics. Now, one of the properties or one of the phenomena in physical optics is called diffraction. And so in this chapter, we're going to learn about diffraction. We'll also learn about polarization. Diffraction is interesting because all waves diffract. Sound waves diffract, light waves diffract. We're going to study the diffraction of light in this chapter. But even physical water waves diffract. And what that means is that when the wave encounters a small gap, it spreads out from the gap. Now, in order for diffraction to be noticeable, the gap size has to be comparable to the wavelength of the particular wave. If it's much too large in relation to the wavelength, there won't be noticeable diffraction. But as we can see, like with these two diagrams down below, when the gap size is comparable to the wavelength, you will get noticeable diffraction, and also the smaller the gap in relation to the wavelength, the greater the observable diffraction effects will be. Now, that was diffraction. We're going to talk more about that later, but let's first talk about another aspect of physical optics, which is polarization. And polarization is the kind of thing that you just can't explain if light is only a particle. The only way that polarization makes sense is if light is a wave. So let's review a little bit about the wave properties of light. We talked earlier in an earlier chapter about how light consists of an electric field perpendicular to a magnetic field. That's why we call it electromagnetic radiation. And each field propagates the other, so it kind of just goes on for infinity unless something stops it. And when you have light, what we define is a polarization direction, which is the plane of the electric field. So by convention, we consider the polarization direction as the plane of the electric field of the electromagnetic radiation in question. Now, polarized light has its electric fields all in the same direction. Unpolarized light has its electric fields in random directions. Most of the light we see is unpolarized or partly polarized. We don't often see fully polarized light. That's available with artificial means that I'm going to explain in a bit. But light, when it just comes from a source such as the sun, is unpolarized. It's the planes of polarization are in all random directions. When we polarize light, we limit that light to one plane of polarization. A good analogy for polarized light is this mechanical analogy of a wave on a string passing through a wooden panel that has a slot or a slit. The wave can pass through if that slit lines up with the plane of up and down motion, but it will not pass through if the slit is 90 degrees to that plane. It will just get blocked. Now, something similar happens when we polarize light. If an unpolarized beam is passed through a polarizer, the transmitted intensity is half the initial intensity. All right, so a polarizer, often called a Polaroid, is a piece of material that has very fine slits in it on the molecular level. You can't see those slits with your naked eye. And what those slits do is they block the light of other planes of polarization and only allow through the light that is of a plane of polarization that matches the polarizer. Okay, so this theta, we call the transmission axis, is the angle that the polarizer makes with the vertical. Notice that unpolarized light comes through, and what passes through is the polarized transmitted beam.
whose intensity is 1/2 of the original. Now, you might be thinking, wow, 1/2 is more than I would expect because only one plane is being allowed to go through. What about all the other planes? What you have to keep in mind, though, is that I'm kind of tracing it now with the mouse arrow. Everything I'm tracing also has slits. And if light is incident to the whole polarizer, well, what happens is the components of all the other planes of polarization, the components that line up with this plane of polarization, they will reform into a new wave that gets transmitted past the polarizer. So really what you're getting is, even though they're only showing one arrow here, it could have shown a bunch of arrows which consist of all the components of the unpolarized incident beam reforming after they pass through the polarizer into plane polarized light. And that intensity is half of the incident beams. The polarizer will transmit the component of light in the polarization direction. So notice that if I have vertically polarized light here, because that vertically polarized light has already passed through a polarizer, and then it goes through a second polarizer, well, then I'm going to get a new plane of polarization, and I'm going to get a new intensity, which is I/O cosine squared theta. Now, again, more lines could have been drawn up and down here, and they're not drawn for the sake of simplicity, but what I'm tracing now with the mouse arrow would be where those lines could be drawn, which means that each one of those, a part of each one of those passes through the direction or the plane of polarization of the second polarizer, and so you're going to get a bunch of transmitted parts of that wave that go through on the other side. Now, this is called the law of Malus, and the law of Malus states that when you pass through, or when you pass light through a second polarizer, well, the intensity that you're going to get is I/O cosine squared theta. Now, that I/O doesn't refer to the original intensity of the unpolarized beam. It refers to the intensity of whatever polarized beam is incident on the second polarizer. So that would be something like this. So take a look at this. We've got unpolarized light comes through, and intensity gets chopped by half, or chopped in half, so we can see this is 1/2 I/O. But then that same 1/2 I/O has to be multiplied by cosine squared theta, so it gets further dimmed. But this 1/2 I/O is what passed through it in the first place. So if I circle this 1/2 I/O is what was on this side over here, this 1/2 I/O. But in the law of Malus, this I/O simply refers to whatever light or whatever intensity reached the second polarizer. So don't be confused by that. The law of Malus has I/O there in its definition. But in this particular case where we have two polarizers, the final transmitted beam is going to have an intensity of 1/2 I/O, because 1/2 I/O is what went through the analyzer. Now, polarizer and analyzer are really the same thing. It's just that we usually give that term analyzer to the second or third in a series of polarizers. If we were to put 3 or 4 or 5 or 6 polarizers, analyzers in a row, of course, we would be able to find the intensity of the eventual transmitted beam with Malus's law. Now, most polarizers are called Polaroids, named after the Polaroid Corporation, founded by Edwin Land, May 7, 1909. And you may be familiar with Polaroid cameras, which were developed by the Polaroid Corporation. And it's interesting how that word Polaroid has become a part of daily vocabulary, especially in physics when we're talking about polarizers, and often we call them Polaroids. because that was the name of the corporation. Now, a very important application of polarization is liquid crystal displays. So LCDs use liquid crystals whose direction of polarization can be rotated depending on the voltage across them. And we're going to see an example now of that. I'm going to show you a little video that does a good animation to help you visualize this phenomenon. But basically what happens is that if an unpolarized incident beam comes through a first polarizer, we have it vertically polarized. Passes through a liquid crystal cell. When that is off, okay, what we get is a transmitted beam, because what happens is that this liquid crystal cell twists in a way that allows the light to bend around to get through the plane of polarization of the second polarizer, or the analyzer. Now, when it's on, that is, when a voltage is applied across the liquid crystal cell, as we see in the bottom frame, what you have is you have no twisting of the molecule, and then the light comes through vertically, and it comes through vertically after it passes through the liquid crystals. And notice that vertically polarized light cannot pass through the horizontal analyzer. So ironically, when a voltage is passed through a liquid crystal, you're not getting any transmitted light. When it's off, you're getting transmitted light. Our intuition would kind of dictate the opposite, but this is the way it works. All right, I'm going to show you a little animation of a liquid crystal display. Okay, so what we have here then is we have a representation of LCD, and it's represented by the hot dogs. The hot dogs just represent the liquid crystals, which behave in a very specific way when voltage is applied across them. Okay, so look, when voltage is applied across them, they line up like that. When the voltage is taken away, they twist. Here's an incident beam, comes through that horizontal plane of polarization. Because of the twist, every time a component is getting polarized in a different direction, so that it passes through the analyzer. Now, when the switch is closed, the voltage is passing through the liquid crystals. So watch what happens to the incident beam. Comes through, and since there's no twisting of the molecule, it goes to the analyzer, which is at 90 degrees in its plane of polarization, and no light gets transmitted. So an LCD screen consists of all of these put together, thousands and thousands of them, with which you can make different images. Now when you add RGB, so you have color in the liquid crystals, you have a red portion, a green portion, and a blue portion side by side, but since they're so close together, your eye can't distinguish them, and all you end up seeing is the mixing of colors that we take for granted on the screens that we use every day. Anyway, I thought that is pretty well done, so I wanted to show it to you. Okay, now how can polarization happen? Well, polarization can happen artificially with polarizers, but it can also happen naturally. So unpolarized light can be partially or completely polarized by scattering from atoms or molecules, which act as small antennas. If the light is already polarized, its transmission will depend on its polarization. All right, so this happens especially by the scattering of blue light in the atmosphere. And we already talked about the scattering of blue light. Blue light scatters much more efficiently than red light, and so because of that, when we look up at the sky during the daylight hours, especially closer to noon, before late afternoon, what we're seeing is the blue, because that blue light is scattered so efficiently. Well, what happens when you scatter or when the blue light gets scattered, is that it also polarizes. And it polarizes because of the orientation of the molecules. If the molecules get excited by a polarized incident beam, then whatever radiation the molecule re-emits in the scattering will also be polarized. Now, let's look here on the right. What happens is at the very upper parts of the atmosphere, the unpolarized incident sunlight hits molecules, and most of the light that gets scattered is going to be also unpolarized. But a small portion will be polarized because of the particular vibration state of the molecule at the moment when the incident beam hits it. And then this, in turn, that little bit of light, that small portion of light that is polarized, will then hit other molecules, almost like a chain reaction. And every molecule that it hits is also going to scatter polarized light. So the light that we see, the blue light that we see, is partially polarized naturally in the atmosphere. This means that sunlight will be polarized depending on the angle our line of sight makes with the direction to the sun. Okay, so this diagram can be confusing. Don't think of it as two people on the beach at the same time. That's not the case. What we have here is we have two different moments of the day. Let's start with the guy standing on top of the sand dune there. And he's standing on top of the sand dune. It's sunset. This lady isn't here, right? We're just kind of combining two diagrams in one. So let's just concentrate on this guy and forget about her for now. The low angle light, reddish, as we talked about in an earlier chapter, is mainly unpolarized because red light doesn't scatter efficiently. Very little of it scatters. And most of it just comes through unpolarized because it hasn't had a chance to polarize naturally in the scattering of the molecules. And so what he's going to see is mainly unpolarized light. Now, let's forget about him and focus on her and forget about the sun over here, because from her perspective, while it's a different part of the day and the sun is all up here, like near the PO of polarization that I'm circling with the mouse arrow. Okay, so the sun's up there. What she's seeing is the blue light scattered in the atmosphere, which is partially polarized. And so what reaches her eyes is partially polarized light, since the light has been polarized naturally through the scattering of blue light. Now, polarization can also occur when light reflects from a smooth surface, and this is why we have polarized sunglasses. Because when light reflects from a smooth surface, especially a non-metallic surface, it tends to polarize in the direction or in a plane that's parallel to the thing that is reflecting off of. Okay, so if the ocean here is flat, obviously, well, that flat surface, flat horizontal surface, means that the light that bounces off it is polarized in that same plane. So the light that creates glare is mainly polarized. This is why we have polarized sunglasses, especially fishermen use it, because that glare makes it hard to see what's below the surface of the water, things such as fish, especially if you're fly fishing. And so polarized sunglasses help you to see what's directly below the water because they can have a plane of polarization that blocks out most of this naturally polarized light. All right, we're going to talk about diffraction. And by the way, polarization is an interesting phenomenon. I'm going to show you some demos in class that have examples of polarization and specific applications of polarization. So I'll definitely show you those later. For now, though, we're going to move into the concept of diffraction. And before we do that, we have to review wave behavior, which we talked about briefly in Chapter 11. So if two waves occupy the same space, their amplitudes add at each point. They may interfere either constructively or destructively. Okay, so let's say we have two waves here, and notice that the crests line up and the troughs line up. And because of that, when we add the two waves together, the crests are extra high and the troughs are extra low because we're simply adding up those magnitudes. Now, what happens if the difference is only lambda, or one wavelength? Well, if it's one wavelength to the right or to the left, it doesn't matter, we're going to get the same constructive interference because crests line up with crests and troughs line up with troughs. But looking over here at this third diagram, what we have is two waves that are out of phase, that, in other words, not lined up, by an amount of 1/2 wavelength. And because they're out of phase by 1/2 wavelength, look at what happens when we add them. We add something that's highly positive to something that's highly negative, becomes 0. We add 0 to 0, becomes 0. We add something highly negative to something highly positive, becomes 0. And so we get complete cancellation of the wave. This is called destructive interference. It doesn't mean that the wave doesn't propagate. It just means that in that particular spot where they're interfering with each other, they cancel each other out. Interference is only noticeable if the light sources are monochromatic, so all the light has the same wavelength, and coherent. Different sources maintain the same phase relationship over space and time. And the best way to get monochromatic and coherent light is laser beams. Laser beams are one color, and that means that whatever electromagnetic radiation comes out of the laser beam is of the same wavelength and coherent. It means that they're all in the same phase. All those light beams that come out are in the same phase. Now, if this is true, interference will be constructive where the two waves are in phase and destructive where they are out of phase. This is true of light waves. It's true also of any wave. Okay, so now we're going to start to understand a little bit how light behaves and how different light waves can interfere with each other. So let's pretend that we have two light sources here. And interference will be constructive where the path lengths differ by an integral number of wavelengths, and destructive where they differ by a half-odd integral number of wavelengths. All that means is, okay, let's say that we have L1 here and L2. L1 comes from one light source, and L2 comes from another light source, and they both meet up at P1. Okay, well, if they meet up, I'm going to go back. If they meet up in such a way that they're in phase with each other, we're going to get constructive interference. But if they meet up in such a way that they're out of phase with each other by 1/2 lambda, we're going to get destructive interference. And so what happens is that when light travels from two different sources, it has two different paths. Notice how the length of L1 is not the same as the length of L2. And so what that means is, since the light's paths are different, since the magnitude of those lengths is different, then we can get lining up of crests and troughs, or we could get the opposite, the destruction of crests and troughs. And all that's determined by, go back one more time, by this pattern here that I explained. Okay. Now, to summarize, the two path lengths, L1 and L2, will interfere constructively or destructively according to the following. If L2 minus L1, which is the difference in path length, is some multiple of lambda, we get constructive interference. If the difference in path length, L2 minus L1, is some multiple of half lambda, then we're going to get destructive interference. And that's all that these two equations mean. However, they're important for understanding the diffraction experiments that we're about to see. Now, the revolutionary experiment regarding the wave nature of light was performed by Thomas Young. Thomas Young was a fascinating person. He was a British scientist, and he was a scientist really of all kinds. By profession, he was a doctor, a medical doctor, and he took his medical profession very seriously. But he also did so many experiments in all different kinds of science, including physics. And one of his greatest contributions was the Two-Slit experiment that he used to prove the wave nature of light. Now, keep in mind, this is about 100 years after Isaac Newton. Isaac Newton was late 17th century, and Young was born in the late 18th century. But as we're going to see, his experiment basically showed, without doubt, that light has wave-like properties. Okay, so how did the experiment work? Well, in the days of Young, there were no lasers, and so there was no easy way to get coherent light. You could get monochromatic light by passing it through a filter, a colored filter, but it was very difficult to get coherent light. Now, what Young did was ingenious. He passed a light source through a single slit, a very narrow single slit, which basically allowed only light beams that were in phase with each other to pass through. It'd be like if you were doing some if you were running track, running a race, and you have 8 lanes of hurdles, and you're running against other hurdlers. Except not only are you jumping over the hurdles, but there's also a low ceiling that you could bump your head on. So you've got to jump just the right amount. Well, if 2 track runners are going neck and neck, and they jump just right, they're both going to pass through the hurdle. But if one jumps too low, he'll get stuck. If one jumps too high, he'll get stuck. And so the only ones that can pass through the obstacle are those who are in phase with each other. It's pretty much what happens with a single slit here, which means that Young found a way to get coherent light. Now, the real magic happened when the light passed through these double slits, because if light is only a particle that travels in straight lines, which was the prevailing theory, then what you should get on the projection screen is you should just get 2 strips of light, right? Makes sense. 2 slits, 2 strips of light. Not a big deal. But what Young found was that he got a pattern of dark and light fringes, which was different from what would be expected according to the pure particle theory of light. Now, let's understand why this happened. Young was convinced when he set up this experiment, he was already convinced or had an intuition that light was a wave. And, a contemporary of Isaac Newton in the late 17th century was Christian Huygens. And Christian Huygens, a Dutch physicist, had also theorized that light was a wave, but Newton's theory had prevailed. Now, Young wanted to think of a way that he could show that light was a wave, and this was the best way he came up with, because Young knew about diffraction of waves. And diffraction of waves, such as this pattern, this can be observed like in a ripple tank or in a jetty in the ocean. If there's a jetty with spaces between it, it's clear that waves diffract in this pattern. And so Young thought, well, if light's a wave, then it's going to do this too. And so his way of testing it was to set up the double slit experiment. Now notice what this will cause. If light's a wave, you're going to get constructive interference where crest meets crest. Okay, so I'm going to indicate that with like a little dot here. This is crest meeting crest. This is crest meeting crest. This is crest meeting crest. Or how about when trough meets trough? Well, this is when trough meets trough right there. Here's when trough meets trough. Okay, but the point is, you're going to get constructive and destructive interference depending on which point in space you look at, if light indeed is a wave, and it's going to behave that way when it passes through the slit. So it was an ingenious experiment. Now, before we talk about the actual pattern on the screen, let's talk a little bit about the math behind it. So I'm going to go back really fast to this image. Notice that if we look at the projection screen, got this pattern here. And that pattern there shows that we have obviously more than two light slits or 2 light projections. We've got many. And so what's the math behind that? Well, the path difference between 2 paths of light that are going to the same spot is d sine theta. And that would be in the condition for bright fringes is d sine theta equals m lambda. Now, go ahead and copy those two equations down. And I'm going to tell you in just a second where the d sine theta comes from. All right, so let's look at these two light beams. We've got two light beams headed towards a certain spot on the projection screen. Now, since that spot is much farther away from the screen than these two slits are from each other, because remember, this is kind of a really zoomed in view, then these light beams are basically parallel. It's like when you go out into the sun. The light beams that hit you are basically parallel because they're coming from so far away. Well, if the projection screen is distant from the two slits, such that that distance is much greater than this little d, we can treat these rays as effectively parallel. And the slight deviation from parallel that there may be is not enough to make any difference in the derivation of the formulas. Okay, so we have the light beam on top, the light beam on the bottom. Notice that if we draw a right triangle here, we can do that right now. So what I'm tracing is, I'm tracing out a right triangle, and this right triangle shows you the difference in path length. Okay, so if the hypotenuse is d and this angle here is theta, then clearly what we have is the opposite, or the side opposite theta, is going to be d sine theta, because sine is opposite over hypotenuse. Okay, so that means the difference in path length is d sine theta. Now, when the difference in path length is a multiple of half lambda, we're going to get destructive interference, and that means a dark fringe. When the difference in path length is a multiple of lambda, we'll get constructive interference, and that's going to give us a bright fringe. Okay, so that's where the d sine theta comes from. Now, all of this is basically showing, and this is the important result of Young's experiment. Young wanted to show that light passing through a slit will behave like a water wave passing through a slit. And that is that the wave will pass through, but it will spread out. And this is exactly what diffraction means. Diffraction is the spreading out of a wave that passes through an opening in a barrier. Diffraction will only occur when the separation, or the length of that slit, is comparable to the wavelength of the wave that's passing through it. So in order to see the diffraction of light, you need pretty thin slits. Now, how does diffraction apply to the two-slit experiment? Well, the way it applies is that we already derived the math for it by the difference in path length thing. But now let's understand the concept behind it by looking at the wave patterns. So light waves spread out as they go through slits, and what that'll get you is you're going to get bright fringes where those crests and troughs line up, but you're going to get dark fringes where they cancel each other out. Look at this animation. And for this animation, we're going to start by using the analogy of water for light. And it's actually a good analogy because waves that propagate through water have many of the same characteristics of light waves and sound waves. And all waves, as we're going to see, diffract. Okay, so let's say that we're just dropping water into a sink, and the sink is filled up, and every time a new drop comes in and the overflow goes into the overflow drain, well, a ripple is created. Now, if I increase the frequency of the drops, then I'm increasing the frequency of the waves. And I can see that there are dark parts and there are light parts. We can say that the light parts correspond to the crests of the wave, and the dark parts correspond to the troughs of the waves. Now, the amplitude can also increase or decrease. If I decrease it, same frequency, but notice that the light parts aren't as light, the dark parts aren't as dark, because the crests are lower and the troughs are higher. This is amplitude. Now I can increase amplitude as well. These big old drops. These big old drops come down, and I have huge ripples. Alright, so that's just frequency and amplitude. I'm going to use some medium ones for the next thing I'll show you, which is two-slit diffraction. Okay, so if I put two slits over here, notice that what I can get is I can get this diffraction pattern. So I get this diffraction pattern, and you can see what the waves do when they propagate past it. I'm going to increase the amplitude a little bit. And notice what we have here. We have areas of constructive interference, like what my mouse arrow is going over right now. And I have areas of destructive interference. This little area here, where it appears that there is nothing. And that's because we have full destructive interference along these lines. Alright, so I can experiment with different separations. With that type of separation, I can see the effect even more, and also different slit openings. But the point is that when I have diffraction through two slits, I am getting both constructive and destructive interference. Okay, so let's see this with light. So if I've got, let's say I'm using laser light here because it's monochromatic and coherent, and maybe I'll use one that's a little easier to see, green lasers. And I can have the amplitude a little bit bigger so that it's also a little easier to see. And now I'm going to introduce the double slit. And as you can see, it's behaving a lot like the water waves. Increase the separation a little bit, and then I'll increase the amplitude even more. Okay, so if you take a look at this, what you can see is you can see the waves diffracting out of the openings, and you can see areas of constructive interference and destructive interference. Now when I show the screen, that shows you the dark and light fringes and how those correspond to the areas we're talking about. Notice that, okay, so look at the mouse arrow right now. I'm tracing an area of constructive interference where the crests and the troughs of the waves are in phase with each other. And notice that where that area of constructive interference that we're following in the ripple, where that ends up on the screen, is a light spot. Now let's take a look at a dark spot. Dark spot is this kind of area here that I'm tracing out, where you can see it's this shadowy area between the two areas of rough or of constructive interference, and that shadowy area where there appears to be nothing, no amplitude, that is an area of destructive interference, which corresponds to a dark fringe. So all of this just to help us visualize what's going on with the wave-like properties of light when we have diffraction. Now, an interesting thing that we're going to talk about next is single-slit diffraction. Single-slit diffraction is a little bit harder to understand, because what we have here is we have light that's actually going from different places within the slit. So we could have, for example, a beam from this top part of the slit, another beam from the middle part of the slit, another beam from the bottom part of the slit, and depending on where those beams go, we get a diffraction pattern on the screen. So I'm going to increase the slit, and now I'm going to, so notice when we increase the slit we just get really a single bright area in the middle, and it's pretty hard to see the other areas. And that's because the slit is pretty large in reference to the wavelength of the wave propagating through the slit. When I shrink it, I'm going to get more of a diffraction or visible diffraction pattern like that. And notice how it's mostly dark here. It's mostly dark because most of the light is getting blocked. Increase it a little bit, and I can see there's going to be this central bright region, but there will also be different dark fringes that I can see. Because what's happening is, you could say that the light is interfering with itself. And it's interfering with itself because the light can travel through different parts of the slit. Alright, so let's continue where we left off. Diffraction is why we can hear sound even though we are not in a straight line from the source. Sound waves will diffract around doors, corners, and other barriers. The amount of diffraction depends on the wavelength, which is why we can hear around corners but not see around them. Alright, this goes back to the idea that diffraction is perceivable when the wavelength is comparable to the size of the obstruction. Now, the wavelength of sound is much greater than the wavelength of light. Because of that, when sound travels around large barriers, it can diffract around those. When light hits a large barrier, it does not diffract around it. It just gets blocked because the wavelength isn't comparable. So let's look at single slit diffraction, which we briefly mentioned in that animation. To investigate the diffraction of light, we consider what happens when light passes through a very narrow slit. As the figure indicates, what we see on the screen is a single slit diffraction pattern. So the main difference between a single slit diffraction pattern and a double slit diffraction pattern is that the central bright region is always very different and significantly brighter than the other bright spots. And it makes sense because most of the light does just go straight up the middle. Now, this slide is really to explain why single slit diffraction happens. On the most microscopic quantum level, what we could say is that really the photons are going in all kinds of different random directions, and at the quantum level, randomness is simply part of existence. This is something that Einstein couldn't quite accept, even though of course he was brilliant and dead right about most things. But one thing he couldn't quite accept is that randomness is simply built in to the universe. And we see this on the atomic level and on the level of light, is that random things happen. Like electrons, for example. They're randomly in their different orbital states, but their exact position is always subject to chance. And photons, where the photon will go, which way it will go, is subject to chance on the most microscopic, smallest level possible. Now that chance doesn't show up on the macroscopic level because things just appear to move in straight lines, but actually what's going on here is an incident beam. So this incident beam comes through a single slit. Some of that light is going to just head up this way. Okay, so what I'm tracing now with the mouse arrow is kind of this direction that some of that light is going to go. Some of it is going to go up that way. Some of the light will go straight. Some of the light will go at negative theta, going this way. Some of it will go at 1/2 theta, going this way. And all of that is completely random. And it's happening randomly millions of times per second. But that's because randomness is just built into the very foundation of photons and of atomic physics. Now let's look at this path length thing. Notice that this is pretty similar to what we saw for double slit diffraction, except that now one beam is going from the very top of the slit, another beam is going from midway down the slit. Now, of course, this is just for clarity. There could be also beams going from 1/3 W, 1/6 W, 1/9 W, 3/9 W. That's 1/3 W. 8/7 W. That's 1 1/7 W. 7/8 W. You get the point. I'm just making up random fractions. But the beams can come from any spot within the slit. Okay, so let's just say that we've got a beam coming from the top, another one coming from the middle, and they're going straight up towards the distant projection screen. Again, because that screen is very distant in relation to the slit width, we can consider these as parallel beams. Now, since these parallel beams are proceeding from different spots, there is a path difference. And that path difference is given to us by W over 2 sine theta, just as it was given to us by d sine theta earlier. Now what this will give us is, it's going to give us a dark fringe. And it gives us a dark fringe because W sine theta, which we could say equals 1/2 lambda. Well, if W over 2 sine theta equals 1/2 lambda, then what you have is W sine theta equals lambda. I'm going to write that out. And I'll write that out because this will help remind us of what we saw with double slit diffraction. So what we saw with double slit diffraction is we saw that when there are multiples of 1/2 lambda, so I'll write that out here. And obviously there's an m there, but for simplicity we're just doing the first dark fringe, which is when m is 1. So notice I have 1/2 lambda. Whenever there's multiples of 1/2 lambda, we're going to get destructive interference, as we saw before. Okay, so where does destructive interference occur? Well, W over 2 sine theta gives us the difference in path length. If that adds up to a half lambda multiple, then just doing simple algebra leads us to W sine theta equals lambda. And that's what we get right here. So the first dark fringe occurs when W sine theta equals lambda. Now, why mention the dark fringes first? Because in single slit diffraction, the central bright region is the predominant characteristic. The interesting characteristics are the faint and few dark fringes. The second dark fringe occurs when W sine theta equals 2 lambda. And we can understand that if we think of the D in this case. D is going to be W over 4. In the last case, D was W over 2. But in this case, we're going to have a D of W over 4. That's a really weird W, but this is a hard tool to use. Alright, so W over 4 sine theta is going to equal 1/2 lambda. Because remember, we get destructive interference for multiples of 1/2 lambda. And notice that if we write it that way, where we have 1 over 2 lambda, then we just do simple algebra on it, and you can see where we get W sine theta equals 2 lambda from. Alright, so as I said before, with single slit diffraction, what really matters, or what we're really looking at, is the dark fringes. Those are easier to see. They stand out. They're thin in relation to the predominant bright fringes. In general, then, we have for the dark fringes in a single slit interference pattern, W sine theta equals m lambda. And that's for integer multiples of m. The positive and negative values of m account for the symmetry of the pattern around the center. That just means that that if we look at the single slit, so I'm going to go back one, that means that I'm going to have a certain number of fringes above the center of the slit and a certain number of fringes below the center of the slit, and those will show up on the projection screen. Diffraction fringes can be observed by holding your finger and thumb very close together. Helps not to be too farsighted. All right, so for most people, this is pretty easy to do. So you can do it right now. You may have already done it when you were a kid or something, but put your thumb and forefinger really close together. I'm doing it now as I'm speaking. And look through that. And if you look through that without the skin even touching, you're going to see some diffraction fringes. Basically what you're looking at there is an example of single slit diffraction. You're going to see interference even though light's still passing through, and that will happen if you make the space between your thumb and forefinger thin enough. A system with a large number of slits is called diffraction grating. As the number of slits grows, the peaks become narrower and more intense. Here's the diffraction pattern for 5 slits. So basically, you can think of multi-slit diffraction as just kind of a bigger example of two-slit diffraction. You're going to get the bright fringes and the dark parts as well, depending on interference. And this is definitely more common. Diffraction gratings are more common than just having one slit or two slits. In the lab that we're going to do, we're going to use diffraction gratings and red lasers and green lasers to observe the difference in pattern. But each diffraction grating has different patterns depending on the width of the slits and the number of slits per inch. The positions of the peaks are different for different wavelengths of light. And that makes sense because as we're going to see in the lab, the shorter wavelengths, that is the higher frequency, shorter wavelength light, doesn't spread out as much as the longer wavelength or lower frequency light. Now notice that the condition for constructive interference in the diffraction grating is the same as what we saw for the two-slit experiment, because again, the diffraction grating is really just an expansion of the two-slit experiment. And so again, we have d sine theta equals m lambda for constructive interference. All right, so let's talk a little bit about some common examples of diffraction gratings. One that you've seen before is that little rainbow pattern that you get when you're looking at a CD. And everyone, this is easily observable. If you hold a CD or DVD up to the light, you'll see all kinds of different rainbow patterns. And that's because depending on the angle, you're going to see different colors since different wavelengths of light diffract differently. Their diffraction angles are different. And basically what we're seeing when we look at the bottom of a CD or DVD is we're looking at light that is passing through those little grooves and then reflecting through those little grooves. But because of path differences, thanks to the grooves, we're going to get diffraction, which is the spreading out of white light into different colors. You probably noticed this in certain insect wings. It's the same exact thing. It's all because of fine grooves on the surface. Now, in certain insect wings and also in certain feathers, we can call these reflection gratings, because a reflection grating is really just another name for a diffraction grating that's reflecting. And so the way that it works in a peacock feather, for example, is you have parallel rods of melanin, and those parallel rods have tiny spaces between them, and thus we can treat those tiny, or look at those tiny spaces as slits. And so really it's a diffraction grating. And we call it a reflection grating because it reflects all kinds of different colors depending on the angle at which you look at it. The last example of diffraction gratings is X-ray diffraction. And X-ray diffraction is used to determine crystal structure. Now, you do need to use X-rays because what we're talking about when we're dealing with crystals is we're talking about very, very fine slits, which really are only going to diffract frequencies of electromagnetic radiation that are high enough, which means that the wavelength is low enough to be comparable to those little slits. Regular light is not. Regular light has a wavelength that is much too high, and so it's not a wavelength comparable to the size of the slits.
The homework is Project Report 3. Hope you're doing well on the projects. And as usual, you can consult the guidelines that I posted for dates and other information. See you in class.